Hello everyone, and welcome back to Virtual Thermodynamics. This will be our last lecture looking at different cycle examples, and we'll be looking at a vapor compression heat pump. Now remember, VC heat pumps ultimately are the same as refrigerators. The only difference is the energy benefit. So in heat pumps, we're interested in transferring heat from the condenser to the hot side of our system. But if this was a refrigerator problem, we would do almost the exact same process, but we would be interested in the heat that's going into our evaporator on the cold side of our system. If we look at a TS diagram of this cycle, it looks like a Rankine cycle in reverse. We have from state 1 to state 2, our compressor is increasing the pressure of our working fluid by adding power to the system. So this is done in a compressor, which means we have to plug it into the wall to get that power. Then, as we go from 2 to 3, we have a heat exchange process at constant pressure, and in this case, constant temperature in this picture because we're under the vapor dome. Then we're condensing the liquid. Maybe we'll get to a saturated liquid. And then we move through a valve. The valve is kind of, I guess, a heat pump or refrigeration cycle's answer to a turbine. So here, instead of trying to generate power like we would in a turbine, we're going to go through an expansion valve. And we'll assume that as we go through the expansion valve, we have an isenthalpic process where the H values stay the same, so that H4 is equal to H3. Then, as we move through the evaporator, we add heat and we increase the quality of the fluid. Because this is a heat pump cycle, our energy benefit is the energy that's transferred from the condenser to the hot side of our system. If we're looking at characterizing this particular cycle, we talk about coefficients of performance because they're greater than 1, so they're not efficiencies, but it's still the desired energy effect divided by the energy cost. In this case, Q hot over W dot net. We can compare that to a Carnot efficiency or a Carnot coefficient of performance for these cycles, where that will be T hot divided by T hot minus T cold. Now it's important in the numerator, and I would say in the whole problem, to use an absolute temperature. So anytime we have an equation where a temperature stands alone, where it's not a temperature difference, we need to use absolute temperatures, because you'll get a very different answer if you plug in 0 degrees Celsius versus 273 degrees Kelvin. So what do we do for cycle problems? Even if we don't know what we're doing, we'll draw a control volume around each component in our system. We'll do conservation of mass. Then we'll see what happens to the energy, so a first law analysis. And if we're designing something, we might want to see if the system can actually happen in real life, so we'd look at a second law analysis. I want to get a symbolic solution, and then I want to ask what's the fluid so that I can fix my states and get my values for specific enthalpy in this case, or specific internal energy if I'm doing a closed system analysis. Conservation of mass in this cycle is fairly simple. We're not splitting the mass like we did in Rankine regeneration. So if the system is at steady state, and all components have one inlet and one outlet, there ends up only being one mass flow rate in the entire system. We can do a first law analysis on all the different components. We'll make the assumptions below for every component, looking to see whether or not we're adiabatic or passive in each component. And maybe if it's a nozzle, we'll then say that it's isenthalpic or that H does not change. If we need to, we can also do a second law analysis and make sure that the process is possible by ensuring that our entropy generation term is positive. Then in this cycle, we'll ask ourselves, what's the fluid? And we can use that information to fix states and find enthalpies and or entropies. In this case, we'll be looking at a refrigerant, so we'll know that then we need to know the phase of the refrigerant. Is it subcooled or a two-phase mixture or a superheated vapor? And if the working fluid is ideal gas, then we have to ask ourselves, do we have constant specific heat or variable specific heat? How do we find H or delta H? We can look at charts like the one for R134A in the FE handbook. We can look at refrigerant tables in our textbook. We can look for ideal compressors or turbines such that they're isentropic processes where S does not change. We can use isentropic efficiencies for turbines or compressors. Or we can, in this case, look for an isenthalpic valve where delta H is 0 across the valve. If we're looking for S or delta S, we have many of the same processes that we can use. For this particular problem, we will solve it using a pH diagram. So here we remember that these are really just vapor dome diagrams, and we're trying to fix the states by finding two independent intensive properties. Each of those properties will correspond to a line on a graph like this. So if we trace both of those lines, the intersection will be where we put our state point. So in this problem, we have a heat pump cycle in imperial units. So we always have to be a little bit careful when we're doing imperial units because it might change some of how we do the problem. We're given some state information and we're asked to find the mass flow rate, the compressor power, the coefficient of performance, and the isentropic efficiency of the compressor. So we'll start with our pH diagram. So here we have to make sure that we're taking a diagram that's using imperial units. So here my entropy is given, or my enthalpy is given in BTU per pound mass. And our pressure is given in pounds per square inch. A refers to absolute. I'm going to start by fixing state 2. In state 2, I know that the pressure is 200 psi and that the temperature is 180 degrees Fahrenheit. I draw both of these lines on my graph. I see where they intersect, and I put my state point there. This is the real exit of the compressor. Next, I'm going to find state 3, which is at the same pressure, but at 110 degrees Fahrenheit. This is to the left of state 2, which is what I would expect. Next, we're going to see that we have a line for 0 degrees Fahrenheit. We know that as we go through our valve between 3 and 4, we have an isenthalpic process, or that enthalpy is constant. That means I can just draw a vertical line down from state 3 to fix state 4. I know that state 1 is at the same temperature, but that the quality is 1. Now, the next thing that I need to do is find state 2s, or the isentropic exit, or the exit of an isentropic compressor. So in that case, I have to draw a constant entropy line. This is a little bit difficult to do. As we look in here, we have two lines of constant entropy, but the slopes are slightly different. So here I try to split the difference between those two lines, and that I'm taking as my constant entropy line, and that gives me state 2s. So when I do this, I have all the states that I need: 1, 2s, 2, 3, and 4. Now I'll use the graph to read the enthalpies. State 3 and state 4 have an enthalpy of approximately 45 BTU per pound mass. State 1 has an enthalpy of approximately 100 BTU per pound mass. State 2s is at approximately 120 BTU per pound mass. And H2 is approximately 133 BTU per pound mass. It's important to remember that I'm just doing this graphically, so there's certainly more uncertainty that's related to my answers here. It's also important to remember that the datums, or the 0 points for H, are different on this graph than they are on a textbook table. So I have to do the problem either all with tables in the textbook or all with the chart. Otherwise, I'll get answers that don't work. My first law in imperial units looks like this. I'm at steady state, one inlet, one outlet, no kinetic or potential energy changes. I'm going to assume that the process is passive when I look at the condenser, and that there's no friction losses and no heat loss in the lines. When I'm looking at the condenser, then I get an expression for m dot. It's Q2 to 3 over H3 minus H2. So I'm using the condenser here because I'm told how much heat is being exhausted here. So now I know what my values are, and I put them into my calculator, and I can find a mass flow rate of about 682 pound mass per hour. Now I can look at the compressor because I've been asked for the compressor power. I can make the assumptions that I'd normally make in a compressor, and I get an expression that I'm used to, that the power is equal to m dot times H1 minus H2. I don't worry about the sign here. I let the first law take care of the sign. Now I notice that the compressor power is negative, but that's what I'd expect because the compressor is consuming power. I plug it into the wall. I want to get my answer in horsepower here, so I have to convert from BTU per hour to horsepower. And we can see that my compressor power is 8.8 horsepower. Next, I'm asked to find the isentropic efficiency of the compressor. Here, I take the ideal compressor, which is going to consume less power, divided by the real compressor, which consumes more power. If I was doing this, there'd be m dots on both the numerator and the denominator. But since the mass flow rate is the same, they cancel out. I can put numbers in here, and I see that the isentropic efficiency of the compressor is just under 61%. Next, I find the coefficient of performance of my cycle. That's going to be the desired energy effect divided by the energy cost, or Q hot over net work. Q hot I've already calculated. Net work is essentially my compressor work, or power, plus my work done by the valve. But the valve doesn't do any work because delta H across the valve is 0. So the net power is also the power of the compressor. In this case, both values are negative. If this was a refrigeration cycle, I wouldn't get this. One value would be positive and the other would be negative. But for the coefficient of performance, I'm always going to take the absolute value. And in this case, the absolute value of the coefficient of performance is 2.67. And that is how you do vapor compression heat pump cycles. Vapor compression refrigeration cycles are essentially the same, just the energy benefit is Q on the cold side. So that concludes our examples for cycle analysis in Introduction to Thermodynamics. I appreciate you watching these videos, and I will see you next time, or at least the next time you watch one of these videos. Thanks very much.